Welcome to Schovia, where we make AI concepts feel like everyday ideas. In the last video, we built a simple OLS model to predict the sales based on TV and radio ad spend. It was clean, it was interpretable, and worked really well as a first step. But now imagine your boss comes to you and says, I want perfect predictions with an error that's almost zero. And that's where trouble starts. To impress your boss, you decide to get fancy. You start adding more and more columns to that simple table. For example, you may add day of the week, is it raining, manager's shoe size, temperature in Antarctica, or phase of the moon. Now you rerun your model and suddenly it looks incredible. On your current data, it hits every point almost perfectly. The error is basically very close to zero. But then next month's data comes in and your supposedly perfect model crashes and burns. Why does that happen? Because it didn't learn the trend. It memorized the noise. This is called overfitting. It's like a student who memorized the answers to one practice test and then failed the real exam because they never actually learned the math. The model learned your data set by heart, but it didn't learn the underlying patterns. Does this make sense? Maybe it's better explained using a visual. Imagine a simple scatter plot. You have your x axis, which is the hours studied, and the y axis with an exam score. And then you plot a bunch of students. The dots are messy, but you can see a general trend, right? Like when studies for more hours, generally they get a higher score. So, first, you draw a simple line that goes through these clouds of points. Some dots are above, some are below. The line doesn't hit everything perfectly, but it clearly captures the trend. You study more and you score higher. Now imagine you're allowed to draw a wild squiggly curve instead of a straight line. You bend the line up, down, left, and right, forcing it to pass through every single dot. On those original students, that squiggly line looks perfect. Zero errors. Every point is exactly on the curve, and then a new student shows up. Let's say that they studied for 5 hours and they scored 75. The simple straight line will probably land somewhere near 75, but the squiggly curve is so wild, it may be way above or below because it spent all its energy weaving through the noise of the old points instead of learning the trend. That wiggly, overly flexible curve is overfitting. In higher dimensions, you don't literally see a squiggly line, but what you see is those gigantic positive and negative weights, which twist the prediction surface in many ways. What you're seeing here is the exploding weights problem drawn as a picture. And that's exactly the situation where regularization steps in. It gently pulls that wild, squiggly curve back towards a smoother one, and those extreme weights back towards something sane. Note that a linear model doesn't typically fit curves, but you could add additional features that are derived from existing features, like square of a feature, or a cube of a feature, or a product of two features, and you can create a squiggly curve. However, discussing polynomial models is not the focus of this video. We'll cover that in another video. The focus here is on regularization, which applies to all situations. So, should we always keep the model simple by taming our weights? Well, that's where the regularization comes in. Think of it as a airline baggage fee. In our OLS video, the last function was just mean squared error. The model could bring in as many heavy bags as it wants. Think about it as big weights. So the behavior becomes complex with more weights, and it could do that for free. But now we change the rules. we define a new loss function that looks like this. So we still care about the prediction error, but we also care about how big and wild the model weights are. We are literally taxing the model for being complicated. If the model wants to make the weight on shoe size equal to 1 million, well, it can, but it has to pay a huge tax in the loss function for the gigantic weight. And because the model is trying to minimize the total loss, it starts thinking, you know what, that huge weight is not worth the cost. I'd rather have a slightly more prediction error and a much smaller weight. This tug of war forces the model to keep the weights reasonable, ignore the junk features, and focus on strong, stable signals, like the TV and the radio ad spend. Regularization turns your model from a desperate memorizer into a calmer, more general learner. There are two popular ways to define this tax, and they behave slightly differently. The first one is ridge regression. It adds a penalty based on the squares of the weights. It shrinks all the weights towards zero so that none of them get outrageously large, but it usually keeps all the features in the model. So ridge is like a shrink ray. Everything gets smaller and better behaved, but almost nothing is completely dropped. The second flavor is the lasso regression. This adds a penalty based on the absolute value of the weights. If a feature isn't really helping, Lasso doesn't just shrink its weight, it can push that weight all the way to zero. A weight of exactly zero means that the feature is effectively deleted. So Lasso is like a ruthless budget cut. TV and radio are useful? Okay, keep them. Shoe size? Nope, goes to zero. If you suspect you have lots of noisy, irrelevant features, Lasso is great for automatically cleaning up your data. There's one more important piece, which is the strength of this penalty. In code, this is usually a hyperparameter called alpha or lambda. You can think of it as how expensive is it to have a large weight. If alpha is too low, the tax is tiny and the model can ignore and overfit. But if alpha is too high, then the tax dominates and the model gets so scared that it shrinks everything too much. And it may end up with all the weights being close to zero, and that's called underfitting. The model is too simple and can capture the real pattern. Your job is to find the Goldilocks zone. Just enough penalty to stop the cheating, but not so much that you crush the real signal. In practice, we usually try different alpha values using validation data or cross validation to see which one gives us the best performance on unseen data. So, putting this together, OLS is a fantastic starting point. It's simple, it's interpretable, and it's great for baselines. Overfitting happens when the model memorizes this noise instead of learning the true pattern, and that may result in huge unstable weights. Regularization is a technique that adds the baggage fee on the loss function, and that helps with penalizing large weights and pushing the model towards more simple general solutions. And there are two flavors of regularization, which are ridge and lasso. You have hyperparameters like alpha or lambda, which are the dial which control how strongly the penalty is applied. If it's too low, you overfit. If it's too high, you underfit. I have posted the Python notebook in the description to show ridge and lasso in action. Go play with the alpha knob and watch what happens to the weights and your model's performance on new data. Thanks for joining us on Schovia Labs. If this helped you see regularization more clearly, hit that subscribe button, and as always, stay curious.